So the first thing I'm going to do is analyze the critical angle. From fiber to air. Fiber to air. So I'll just draw it off to the side here. If I have a light ray incoming from the fiber into the air, what angle of incidence will create an angle of refraction of 90 degrees. I'm just going to analyze that. I'm just going to use n to represent the index of refraction of the fiber. I'm not going to give any subscripts to it because my other medium in this whole situation is air. And for air, I'm not going to write n. I'm just going to use the index of refraction of 1 in my formulas. So critical angle, fiber to air. We'll have n times sine of the critical angle equals 1, that's the index of refraction of the air, times sine of 90 degrees. That's how you determine the critical angle. The critical angle will be the inverse sine of 1 over n. We don't know what n is. Remember, sine of 90 degrees equals to 1, so the right side of the equation is 1. Okay, so I've got equation 1 here. Next, I'm going to analyze the refraction that occurs on the left side of this fiber optic cable. So this angle here, I'm going to call that theta 2. So with Snell's law, we'll have 1 index of refraction of air times sine of 60 degrees is the angle of incidence equals n, the unknown index of refraction of the fiber, times sine of theta 2. Sine of 60 degrees, that is one of the special angles, actually, that equals to root 3 over 2. So theta 2 would be the inverse sine of root 3 over 2n. It's just dividing both sides by n first, and then inverse signing it. So if I make a right angle triangle with this green line here, what I can do is calculate the angle at the top here, which I'll call theta 3. 3 angles in a triangle add up to 180 degrees. So theta 3 would just be 180 degrees minus the 90-degree angle minus theta 2. So that simplifies to 90 degrees minus the inverse sine of root 3 over 2n. Okay, so n is unknown, though. How will we ensure that total internal reflection happens? So here's the key. Total internal reflection, I'll just use TIR for short. Happens if theta 3, the angle up at the top, is bigger than the critical angle. Total internal reflection happens when the angle of incidence is bigger than the critical angle. So therefore, I am looking for when is, if I'll call this equation 3, when is 3 greater than 1. That is what I'm looking for. I'll write the equations out. So 1 is 90 minus inverse sine of root 3 over 2n greater than the inverse sine of 1 over n. And that is a difficult equation to solve, or an inequality. We call it an inequality when it's greater than or less than signs. Yeah, that's a difficult one to solve, but not that difficult for Wolfram alpha. So I'll be typing this in. However, instead of typing in 90 degrees, I'll be typing in pi over 2, because Wolfram alpha is going to automatically use radians. And when I type it in, it gives me an answer that the n value will have to be greater at least 1.32. So any index of a fraction bigger than 1.32 will cause the light to be trapped in the optical fiber for an angle of incidence of 60 degrees. In one of the homework questions, the challenge homework question, they ask to show that if the index is 1.42 or bigger, that the light will always be trapped no matter what angle it enters on the left.